I'm not a physician, I'm a physicist.
A physicist.
Maybe here there are a lot of physicians, but very few physicists.
Yeah. You will be surprised because I was a chair yesterday, and the first presenter was a physicist by training. So I think as a hidden identity.
I'm a converted physicist.
Yeah, and I have a colleague also who is physicist. So at least I know 3. And when I see that we have electricity and water, I already got afraid. Okay. And one personal story, I was responsible for the room. First I was surprised that my colleagues thought that I will have one, but since then, every day when I come to the university, everyone is joking with me with the broom. So why do I need a broom? So yeah, that's
flying.
Yeah, thank you very much. Thank you very much for starting the session. So I give you the floor, and I will stop you as agreed.
Okay. So welcome to everybody. I have to confess that I'm still a physicist. I mean, I teach physics, and actually I teach computer physics to my master students, and also elementary physics and engineering. But I have been invited several times in high schools, and I also teach to elder people in the People University of Florence. And so the problem in teaching physics is that it is not only that the physics is complex, but it is also too similar to real life. I mean, everyone is born with an intimate knowledge of working physics. I mean, the physics of every day, essentially Aristotelic physics. You know that if you don't push continuously something, it will go to stop. And if something is moving by itself, it means it is alive. So you have to be worried about this and so on. So the problem of teaching physics is that you not only have to learn something which is weird, that is full of mathematics, but you have also to forget what you have learned, what you know by heart since you were there. So the problem is how to prove that actually if you investigate more little in detail, life is not what you expect, because clearly it obeys the law of physics and not that Aristotle's. And one way that I discovered for catching the attention and say having the people, the children, to be ready for studying physics for the next 5 minutes is to show some magic trick that may surprise. Essentially, they works almost everywhere except when I teach physics to physicists, because they are too smart. Okay, so let me start quickly. Clearly, this is a reduced part of the show. If you want to see some of them, you have to go to LK8. You can look at it in Google. It is in Italian, but you can find a lot of things, like, for instance, the physics of ducks, which means Walt Disney physics. It is a book in Italian, but where you can find how the little duck, Dewey, discovered how many law of physics they violated during the adventure. And so it is the secret diary where he examines all the law of physics that have been violated and how they can be restored. And there is also a book of mine about Sherlock Holmes and Watson trying to discover where the physics is hidden in everyday life. It is an investigation. Okay, and but in the video section there are a lot of videos where you can see my experience, especially this Pianeta Galileo, my experience with a lot of schools. I have also an article about this experience, and if you are interested, you can drop me an email. Here are some business cards. Okay, let's go. First of all, Titanic. You know the history of Titanic. Have you seen the movie? Yes. Someone has not seen the movie? No, everybody can. So the idea is that Titanic goes with rich people and also poor people, and at a certain point it collides with an iceberg, and it is going to sink, but only 2 people, the smartest one, Jack and Rose, has been able to grab themselves to the bottom part of the ship, and Jack says a crucial thing to Rose. Prepare yourself to swim furiously, because the ship will try to grab up down into the water. In your opinion, is it true that when a ship goes down, makes, say, a turbulence or a whirlpool in the ocean, or not? It is just a fiction, Jack was sailing, say, 2,000 miles under the sea in Capitan Nemo and so on. Votation. This is an interactive section, you have to vote. Is this true? Yes. Who believes it? Yes. Who doesn't believe it? Okay, so let's do an experiment. This is our Titanic here, and this is the level of the ocean. I can mark it here. Okay, now I let this Titanic sink down the water. What will do the level of the ocean? Will it rise, stay the same, go down? There are only two options. So who vote for the level of the ocean to rise up? 1, 2, 3. You have to put $5. Who is voting for it stays the same? 4. And who is voting it will go down? 2. The rest you have to vote. So, again, option A. More. Option B. Option C. Okay, so I'll show you how to make money with this stuff, because the level of the ocean is going down. So why? And because essentially this glass, like the Titanic, is made of a material which is heavier than water. So it has to displace more water than its volume, and this is the reason why it is hollow. It is not only for carrying goods, but also because it has to displace more water than its true volume. If I make it with say clay, and then I wrap it into a ball, it will sink. No? So essentially it can float only because it is empty inside. But clearly, when it is full of water, it's only displacing its glass volume, which is less, and so the water goes down. And so imagine a ship like this that is going down into the water. It is making a hole in the ocean, and so the rest of the ocean is going to fill up this hole, and clearly it can easily grab ships and swimming people. Okay, but you know that our Titanic was full of, say, gold and other valuables, and so there have been a lot of expeditions to recover, I don't know, the money, the iPhones of the rich people, which are, say, at the end of the ocean. So now we have to redo this expedition. I have here a diver. And now I have to convince the diver to go down to the money. Clearly I can do it only with the power of my mind, and I can let it go down. Are you convinced or not? I'm a magician?
Yes, you are.
So I can magnetize almost everything, you see. You're not convinced. Come here. You.
It will magnetize.
I can magnetize even her, so like this. So try to. Oh, it works. So, you want to try? Try to push the... Okay, you can pass it to other people. You believe again in physics, eh? And so why I'm able to make the diver go down just by pressing? Now you have to push. Okay. So what is changing inside? Pressure.
Yes, pressure.
And pressure, what makes it?
Heavier?
Heavier what? The water heavier?
No, the object.
The object heavier? Difficult.
Break the
What is inside this cup? Why it is floating?
Because of the water.
Because it is inside, there is a bubble of air inside the cup. And this is highly compressible. So when I increase the pressure of the water, the bubble is reducing its volume, it is displacing less water. So again, it is Archimedes' law. And so if you calibrate the weight of the diver, you can make it go up and down. You can also make a thermometer. Galileo did similar things because the density of water changes with temperature, and so you can make also a thermometer with this. Okay, but this was the simple experiment. Now something more complex through magic, and so now I'm putting this net. You confirm it is just the standard net. Like this, and sorry, you can put the water inside, and but now with the power of mind, no trick, you can keep the water inside. You want to try? No? Come here. Oh, it's easy.
Probably won't work with me.
No, it works. So you can fill it with the water. Put this on the top. Stay here. And now let me touch it with the power of my. Okay. Uh-oh. Quite easy. Now the difficult part. This one. What do you think about this? Is it possible to keep water inside here?
Doesn't look like it, but probably with physics.
Let's try it. You can go ahead. Thank you. So let's try with this one, which is so quite a different stuff. It's not so easy because of this glass. It has to be extremely straight, and this is not the case, but I'll try to make it work. So, oops. Now the problem is that it has to be extremely horizontal, but actually you can do this. So the problem is actually it is not the size of the holes, because you know that it is possible to keep water inside of this, also a larger tube, without any problem. And so you feel that it is difficult to keep the water inside, but it is not just for the size of the holes. It is because they are all coupled, so that if it is not exactly horizontal, the weight of the rest of the water will go into the hole that is lowest, and so at least is sufficient for braking, because here we are near the limit. No? So for this one you can tolerate such an inclination, and for this you are already near the limit. But it is not just the size. You can do the same experiment I haven't here with a larger
straw.
Straw, and it still works. So the problem is that they are coupled. So essentially physics is not so easy. Okay, so now, okay, let's do it with the air. I probably better dry my hand before. And so, let's try to make some magic with this. So, do you think it is possible to keep this ball in equilibrium on the air? Yes? Okay, come here. So, please. But to make things a bit harder, she cannot see anything. Are you ready?
Yes, I am.
Do you think you are able to keep the... You can watch, You can... So actually, I was thinking, instead of selling air balls with the rope, no? You can just have something like this for having a... No? Now, here it is too powerful, I think, to take this. Okay, you can do this, you can do also this, but okay, you can. The very magic is this one. Not only that I can keep a ball like this, which is somehow easy, but why I can keep it also, this is too heavy,
Yeah.
in an inclined position. You mean, this is not on the vertical. So, why it is not falling down even though it is not on the vertical? Here it is magic. But that's also to do with physics. Or you don't need actually this hair dryer. Maybe better with the smaller one. You can do this also with your lungs. Okay, this one maybe is the best one. Something like this. So why? So instead, before giving the explanation, another question: can I rise this piece of paper with a jet of air? So clearly, like this is too easy. I mean, on putting the straw on the top of the piece of paper.
You can, otherwise you will
By magic. So it is extremely easy. So why? So this is the reason why flags do like this. So essentially, do you have an explanation? Who is pushing up the piece of paper? The same force that is keeping the ball inclined in the stream of air, which is Bernoulli law. I mean, the air is made of a lot of particles that are traveling in all directions, and then they're continuously impacting on my surface, but they are the same on this side and the other side, so it stays like this, or this stays vertical. Now, if I am forcing molecules to have a certain direction, there are less of them that are going in the transverse direction. And so essentially, when I make it like this, there are more particles pushing, so colliding in this direction than in this one. So what is rising my air, so a piece of paper is the air here that continues to push, while I'm removing the molecules that are colliding on the top. And the same is here. There are a flux of air that is more on the top than on the bottom. So here there is rest air that continues to collide, and here I am removing the molecules that are colliding, so it has a net force like this. Clearly, in this direction, this is the opposite. So it is repulsed in this direction, but attracted in the transverse direction, and so it can find an equilibrium position. Okay, so just the last two experiments. This one is due to Einstein. Einstein, the 1917, just after writing the general relativity, and wrote a small article saying, okay, I think that the reason for which the rivers become so tortuous is the same, the reason for which the leaves of tea, that in this case are these pieces of rubber stripe, when you make the tea turn, so they group together at the center of the jar, and in this case you see I have chosen a jar which has a convex bottom, so the gravity makes this piece of say rubber stays on the circumference, and since they are heavier than water, also the centrifugal forces make them stay at the extreme, say, at the peripheral circles. But when I make it turn, and I'll pass to you, they suddenly are pushed into the middle of the jar. And so you can experiment on this. So first of all, you randomize them, then you make water turn. Be careful. Physics is always dangerous.
Computer.
Wait. You see, drawing the sun.
Sorry,
Okay.
So why? This is a difficult problem. Actually, what happens here is that clearly, when water is in rotation, it is not more flat. It takes a parabolic shape. But near the jar, for viscosity, it has to stay at rest. It is the reason for which it stops turning. If you made the same experiment with a super fluid helium, for instance, it never stops turning. So I have to maybe to draw a bit here. So this is your jar. This is the profile of the water, which is turning. But here you have a small part which is at rest, and also in the middle for symmetry, which you have a part which is at rest. Okay, but now you have a circuit of water at rest that connects 2 points which are at different height, and so for the communicating say vessels, low water is falling down and rising up in the middle continuously. I mean, while it turns, it goes like this, and clearly your leaves of tea are carried with the flux of water, and finally they stay here. Since they are heavier than water, they cannot rise. So in a river, if this is the section of a river when it makes the turn, the water cannot be flat. It has to be like this, because it is essentially half of our jar. So when the river is making this kind of turn, so it is higher here than here, but still there is this portion which is at rest, because clearly the bed is at rest, and so the water is continuously making this turn. I mean, it is a spiraling, not like this, and so it continues to erode here and deposit things here. And so when it starts making a turn, it continues making the turn so even in an exaggerated way. And finally, generally, so maybe the river starts like this, then makes things like this, and sometimes it can even cut itself and leave these lakes that are called the bow lakes. So this is the article by Einstein. And so, for finishing the show, I let Giovanna fly with this. No. No. Okay, don't fly, okay. Another experiment, but with the broom. So I need a volunteer here. You? So do you know what the center of mass is? I mean, it is a point in this broom where you can put a finger and keep it in equilibrium.
Yeah.
Okay, try to find it. With just one finger. Okay. So you see, you have to make a lot of experiments. Okay. So now close your eyes. Then open your eyes for a moment. So you have to keep the broom like this.
Yeah. And
then slowly try to close your hand. Don't worry. Because for my magic, the broom is not falling, and your hands will join exactly under the center of mass of the broom. So,
you feel it.
eh?
You feel it very well. Yeah, it's good.
So you have noticed that your hands are.
You can't move this one.
Yeah, you can move this at first. Then at the top you can move this, and this one stays. And finally, they join below the center of mass of the broom, and the broom is not falling. Why?
Because you found the center.
Yes, but why is it not falling? So,
you found the equilibrium, so on both sides is equal mass.
yes, but why? You are not doing anything volunteer, so it is all automatic.
Because there's less force on that side.
Friction.
Yeah.
Friction and momentum. So, I mean, the explanation is the following. Clearly, for being in equilibrium, you need the torque to be the same at the two sides, no? So you mean that the force times the distance from the center of mass, the product of the two, be the same, and you feel here heavier than here, no? Because it has less, less lever, and so it has to push more, and this has to push less. But the friction is proportional to the force with which you push. So this finger has less friction than this one, so it is free to slip until it arrives nearer to the center of mass than the other one. Now it is this one which exerts a higher force, so it is this one who is going to slip, no? And then alternatively one and the other, so automatically they join under the center of mass. So you have to sit here, Giovanna.
Yeah.
The center of mass.
If someone wants to try,
Okay,
you have time.
that's all. Thank you.